Hello Calculus fans, going to make a video where I go through a few work problems that pertain to leaky buckets, and I'll mention ropes. This is something I'm right at the end of our quarter in Calculus 2. This particular topic I've actually done lots of times. If you go in my lecture notes, you can see lots of examples. You can see a one-page summary. You can see basic practice problems. And I have a collection of like 3 leaky bucket problems, 3 rope problems, 3 pumping problems, and I do full solutions. I've made a test prep where I've done solutions. But this is one of those topics that sort of no matter how many materials I make, someone says, can you make a video? So it's just part of it. But this would be probably your best place to go. I had this test prep where I had several problems, and I made a video. So and then I made a practice sheet, a little more challenging practice sheet, and a really challenging practice sheet with solutions. So it's not hard to find problems to practice, but let's do one more kind of end of the term practice, assuming we've done everything. Part of the challenge is the information can be given in lots of ways, but here we go. We have a leaky bucket problem. And maybe I'll just try to say it in another way. It's always pattern finding. Pattern finding is one of the harder skills in math. So they're saying that you're going to lift something 8 meters. And what's hard about this question is they give the information in a lot of small pieces. So it's more about keeping track of things. So what does it say? It says it's going up at 0.5 meters per second. So that was a convoluted way to tell you how much time it's going to take from the top to the bottom. So if this is time 0, you should see that it's going to take 16 seconds to get to the top. If you don't know how I computed that, I did 8 meters divided by 0.5 meters per second to figure it out. But you can also just think about it. Every 2 seconds you're going to go up a meter. And so it's going to take 16 seconds. So I'm just trying to make sense of the information. Initially, so it's not like that part had a formula. You just have to think about it. When it was at the bottom, it was 25 liters. And it's leaking at a constant rate. So no matter what's going on in this question, I now know that the force is probably going to have something to do with a constant rate. And this is how leaky bucket problems go. Usually it either gives you a formula for the weight at a given moment, or you have to find it. And if I re-explain the whole thing, this is going to take forever, but again, the idea is once the thing gets here, if we know the force, we're going to multiply by delta x. That'll tell you the work done in that little segment, and then we'll add all those up, which is what the integral does. Okay, so we're trying to find the pattern based off of x. Let's just make a choice. Let's have this be x equals 0. Let's have this be x equals 8. And so part of the challenge is just finding all the pieces. But to me, the only thing that's missing right now is how much water we have at the top. Once I figure that out, I think I'll be able to find the equation of the line. Now, liters is not weight, but they tell you how to turn it into weight. They say it's 9.8 meters per second times kilograms, so that's 9.8 newtons per liter. So to get the force, it's going to be 9.8 times how many liters there are. So my first comment is it's going to be this, and then I just need to figure out how many liters there are. Dx. So we're trying to find the equation of a line. Anyways, it says you're losing 0.3 liters per second. It's 16 seconds. And so that means you're going to lose 16 times 0.3 liters per second. It's going to be 4.8 liters. So now I know. If you subtract 4.8, I think it's 20. Of course, you can use a calculator on the test. I'm just trying to do this in my head so I can be a little faster. And now we're essentially done. We know the y-intercept is 25 for this line. We just need the slope. The slope is going to be 25 minus 21.5, which is that 2.8, over 0 minus 8. So it's negative 4.8 over 8, which comes out to be negative, I think, 0.6. Negative 0.6. That's it. We're done. So as bad as that question looked, not done. You'd compute it. But it was actually pretty short. And I did it right here. I plugged it in. and I got 101,771. I have to be careful because if I don't check my work on these calculation problems, I'm going to make a mistake and somebody's going to be mad at me on the discussion board. So let's go look, make sure I didn't do something weird. There it is. Okay, was that hard? Yeah, it was a lot of information to sort through, but it was a problem where basically you just had to find the formula for force and you were done. That's what leaky bucket problems are about. The dx represents the distance. Okay, let's go on. I thought I would just make a comment about ropes rather than pull up a particular problem. The most common rope example we had was a rope being pulled all the way to the top. And I told you how I like to think about it, but I know some of you like to do it a different way. So first I'll tell you the other way to think about it. So some students like to think about x as this. So the bottom is x equals 0. And they think about eventually there will be that much rope hanging. And this is what I call the remaining hang approach. Remaining hang. If you think of it that way, you can think of that as a leaky bucket. Just the collective amount that is left. And if you think of the collective amount as one object, then you can think of this as a leaky bucket problem. And you need to figure out what that is and then think about multiplying by delta x. For me, that's harder to think about. So over the years, I don't do that. But the remaining hang force would be 2x because it's 2 pounds per foot. And you'd multiply times delta x. So that's this way of thinking about it. So where you say, this is the remaining hang in pounds at a given time. What I don't like about that is I have to think about an intermediate step along the way. But it makes a lot of sense, and I know a lot of people do it that way. This is feet, those are the bounds. Let's do the other perspective. So I've mentioned the reason I like this other perspective is that it also can be applied to pumping problems, and sometimes those are tough for students. And so by doing the simpler version here, that can sort of help us. So the stack of books problems is to break this up at the beginning into a bunch of subdivisions and then just treat it as if each one of those is a separate problem. Let's just, for example, call this and in these problems, I usually think about x as going this way. So there's the added issue of labeling. So I'll do this both ways. Let's label it x and let's label it y. And we'll talk about this. So if I take a particular subdivision right here, it's going to end up at the top. That subdivision is going to have a force of 2 delta x. Because it's going to be the width or 2 delta y, depending on which variable I'm using, times that. And the rest of the question is going to be distance to the top. Now in the x situation, the distance to the top is x. In the y situation, the distance to the top is 10 minus y. And so this is what you get. This is distance to the top. This is the force if you're doing this one. And if you do the other one, it's 0 to 10, 10 minus y, 2 dy. And all three of these things are the same. Same, same, same. I mean, these two you can definitely see are the same. This one just sort of plugs them in an opposite order. This is going to be x squared from 0 to 10. It's going to be 100 foot-pounds. I don't care how you think about it, but it's one of those. In a given problem, it's kind of nice. What I like about this one is I don't have to draw the intermediate step. I just draw the beginning, the end, and then I focus on just how far does one subdivision go. In any case, it's 100 foot-pounds. Okay, so let's do one right here. We have a cable. Old exam, this is 80 feet. It says to lift 50 pounds of coal up an 80-foot mine shaft. The bottom of the cable weighs 2 pounds per foot. Well, that's weird. So this part from here to here weighs 2 pounds per foot. And the top part weighs 3 pounds per foot. So that's what's different about this one. That's the adaptation. It's going to lift it all the way to the top. Up to the top. Okay, so there we go. So let's draw the ending picture. So at the end, it's going to look like this. So to me, this problem is a little harder to think about as a remaining hang, because once I get to a certain spot and I call this x, the weight of that's going to depend. Once you get past 40, it's going to be 2 pounds per, but before 40, it's going to be, some of it might be 3 pounds, some of it might be 2 pounds. So to me, this problem suggests I would like to do a stack of books. I'm sure there's a way to think about it the other way, but I would like to do this. And let's label the top 0, let's label the middle 40, let's label the bottom 80. And the only bad part about doing this is the 50 pounds won't be part of that discussion. We'll just have to compute that separately. So this is the bad part of my approach. So I would have to do 50 times 80, and that's the work to lift the coal. I wouldn't do any calculus for that. Then I would compute the separate pieces. And I would say for any x value from 0 to 40, what's the pattern? If I take one of these, well, it's the thickness times 3, so it's 3 dx, and then it's the distance. So if you give me a particular x, since x is the distance from the top, it's just x. And then I would have from 40 to 80 a different pattern. The distance to the top would still be x, but it's now going to be 2 dx. So to me, that problem was set up perfectly for my stack of books approach. And so this is going to be 4000 plus 3 halves x squared from 0 to 40 plus x squared from 40 to 80. And we would get whatever that is. 4,000 plus 3 halves of 1,600 plus 6,400 minus 1,600. So half of 1,600, that's 800, so it's 10,400 plus 800, 11,200. I'm sure I did that wrong. Let's check. Okay, we have answers. Ooh, 11,200, I did it. Again, if I was taking the test, I would have taken more time and checked my work. There you go. So stack of books was the best approach. And then someone today asked me about this question, which is a little more convoluted version of a leaky bucket because it has a few more things going on. So it says you're lifting a sandbag. Here's a sandbag. Sand is dripping out. And we need to find, so we now know the mission is to find a formula for the force at a given height. So if I label this, x, we would like to find the force, and then we want to integrate that. But they did not tell us that directly. Instead, they told us the mass. Now we can sort of see a few things here. If I can figure out the formula for the mass, it's going to be the integral from the ground to a height of 2 meters. So it's going to be the integral from 0 to 2 of 9.8 times whatever the mass is. And we're going to see if we can get it all in terms of x. X being the distance from the bottom. So there's a couple little side challenges here. So let's see if I can handle those. But that's the layout. The mass in terms of x. So one little thing is it says it's going up at 0.2 meters per second. So if it's going up at 0.2 meters per second, that means the distance you go up, this x, is going to be 0.2 t. So you had to think about that it's 0.2 meters per second times the number of seconds will be the distance you go up. So that was the added little challenge, but we'll deal with that in a second. The initial mass is 10, and the rate is this. So they slipped in a calculus problem. You have to integrate. Log of 1 plus t plus c. And if you plug in a 0, this is 0, so this has to be 10. Done. So you get m of t is log of 1 plus t, which I know must be positive. But the problem is that's not distance. But you can figure it out because t is x over 0.2. it's going to be 1 plus 0.2x plus 10. So yeah, there's some challenges there, but then you're going to do integration by parts and finish the problem. Okay, let's leave that, and I'll do a separate video about stacks of books.